50,000. Megalodon teeth have been found, but not a single one younger than 3.6 million years. So why do so many people insist the Mariana Trench still hides these ancient giants? The appeal is easy to understand, but the science paints a far stranger picture. Before we dive into myths and internet speculation, let's confront what the evidence really reveals, and what almost everyone is missing. The idea that Megalodon might still be alive, lurking unseen in the ocean's deepest trench, has become a fixture of internet culture. Social media posts and viral videos often show blurry shadows or doctored submarine footage, paired with claims that the Mariana Trench, nearly 11,000 meters deep, could easily hide a giant predator from science. These stories spread fast, fueled by a fascination with the unknown and the thrill of imagining a prehistoric giant evading discovery. The trench's sheer depth and darkness seem to offer the perfect hiding place, a realm beyond the reach of ordinary exploration. But fascination alone doesn't make for a scientific hypothesis. In science, a claim must be testable by evidence. That means looking for physical traces, bones, teeth, DNA, or ecological impacts, rather than relying on the absence of proof as an argument. The Mariana Trench is often described as unexplored or inaccessible, but in reality, scientists have mapped and sampled its depths for decades, applying the same evidence standards used everywhere else in biology and paleontology. The difference between a meme and a hypothesis comes down to evidence. While pop culture thrives on the idea that it's too deep to know for sure, science asks, what should we actually find if a living population of Megalodon existed? Would there be recent fossils, genetic material, or disruptions in the food web? These are the questions that move the legend from speculation into the realm of testable science. And when those standards are applied, the story of Megalodon's possible survival starts to unravel long before the ocean floor comes into play. The fossil record draws a clear boundary for Megalodon's existence. Teeth and vertebrae attributed to this giant shark are found in rock layers dating from the Miocene to the early Pliocene, with the youngest verified specimens locked at about 3.6 million years ago. Paleontologists have cataloged more than 50,000 Megalodon teeth, scattered across every continent except Antarctica. These teeth are not rare, and their abundance is a direct result of the shark's biology. Like modern sharks, Megalodon shed thousands of teeth throughout its life, leaving a trail that should stretch right up to the present if it had survived. But the trail ends abruptly. After 3.6 million years ago, there is a complete absence of Megalodon fossils in younger sediments. This isn't a matter of missing a few stray teeth. Global searches, including targeted digs in well-sampled marine deposits, turn up nothing post-dating the early Pliocene. Even claims of younger teeth have not held up under scrutiny. Careful analysis shows these are either reworked from older layers or misidentified, often mixed with fossils of unmistakably ancient species. Dr. Catalina Pimiento, a leading authority on Megalodon extinction, describes this pattern as a textbook example of a stratigraphic discontinuity, a sharp, undeniable gap in the fossil record. She notes, if Megalodon had survived, we would expect to find its teeth in younger rocks, just as we do with every surviving shark species. Instead, the silence stretches across millions of years. For paleontologists, this gap is not just evidence. It is the strongest argument that Megalodon truly disappeared long before humans ever glimpsed the deep sea. Megalodon was a giant among sharks, reaching lengths of 15 to 20 meters and weighing more than 50 tons. Unlike most modern sharks, it maintained a body temperature several degrees warmer than the surrounding water, a trait called regional endothermy. This adaptation allowed for bursts of speed and long-distance hunting in temperate seas, but it came at a steep cost. Every day, an adult Megalodon needed to consume over 2 tons of prey just to maintain its metabolism. That is the energy equivalent of eating a small whale each day, a demand matched only by the largest marine mammals. Dr. Sora Kim, a paleobiologist who studies ancient shark ecology, explains that this elevated metabolism was both a strength and a vulnerability. Megalodon had an elevated body temperature, which meant it could move fast and hunt big prey, but it also needed a lot more energy to survive. In the warm, food-rich waters of the Miocene and Pliocene, that worked. But in the cold, dark depths of the ocean, such high energy needs become a liability. The biology that once powered the ocean's top predator is fundamentally mismatched to the slow, resource-scarce world of the Hadron Zone. The environment at the bottom of the Mariana Trench is defined by extremes that challenge the very notion of life, let alone the survival of a giant predator. Pressure at Challenger. Deep reaches more than 1,000 times what we experience at sea level, enough to crush the hulls of unprotected submersibles and to denature the proteins in most animal cells. Temperatures hover just above freezing, rarely rising above 2 degrees Celsius. Sunlight never penetrates these depths, so there is no photosynthesis, and as a result, the trench receives less than 1% of the organic material produced at the surface. Food arrives only as a slow rain of detritus, tiny fragments of dead plankton, fish, and marine snow drifting down from above. This meager supply supports a sparse community of scavengers, mostly small amphipods, and gelatinous invertebrates. Large animals are absent because the energy budget simply doesn't add up. A 50-ton predator would need thousands of kilograms of prey each week, but the entire ecosystem of the Hadal Zone produces only a fraction of that. The physical limits, crushing pressure, near-freezing cold, and chronic food scarcity define the trench as a world for specialists, not giants. These facts alone make it clear why the idea of a megalodon hiding here is at odds with what science knows about the deep sea. Expeditions into the Mariana Trench have left a detailed record of what actually lives in the planet's deepest waters. In 1960, the bathyscaphe Trieste descended nearly 11,000 meters, documenting a world of amphipods and simple invertebrates, but nothing larger. Half a century later, James Cameron's solo dive in the deep-sea Challenger repeated the journey with high-definition cameras and real-time telemetry. The images revealed only small, translucent creatures, no sign of large fish, let alone a megashark. Over 100 dives by research submersibles and remotely operated vehicles have since cataloged the trench's inhabitants. The logs are consistent: amphipods, snailfish, jellies, and microbial mats. No large vertebrate predators have been recorded, and not a single bite mark or carcass points to anything bigger. Environmental DNA surveys add another layer. Water samples filtered aboard vessels like the pressure drop, under the guidance of Dr. Alan Jameson, screen for traces of vertebrate life. The results show a genetic fingerprint dominated by invertebrates and small fish. Shark DNA, which would stand out in these tests, is entirely absent. After decades of sampling, the evidence points to a simple fact. If a giant predator still hunted here, its presence would not be a secret. The trench is not a blank slate. It is a well-studied ecosystem with no room for hidden giants. Hydrophones stationed across the Mariana Trench are tuned to pick up the faintest disturbances in the water. These sensors can detect the low-frequency movements of large animals from as far as 15 kilometers away, registering even the subtle pressure waves of a passing whale. If a multi-ton predator were present, its swimming and hunting would create acoustic signatures well above the background noise. Meanwhile, environmental DNA, fragments shed by every living creature, lingers in the water for up to 48 hours before breaking down under pressure and cold. Modern eDNA assays are sensitive enough to reveal the presence of a single large animal within a vast area. Decades of monitoring, both acoustic and genetic, have yet to produce a trace of any giant shark in the trench. Baited landers dropped into the Mariana Trench reveal how quickly life responds to new food sources. When a chunk of tuna is placed at 10,900 meters, swarms of amphipods arrive within 45 seconds. No large predators ever appear, just a flurry of tiny scavengers. Scientists also test the water for trimethylamine, a chemical marker released as animals break down protein. The readings show only trace amounts, matching what you would expect from small invertebrates and fish. If any giant shark were feeding here, both the bait and chemical signatures would tell a different story. In science, extraordinary claims demand extraordinary evidence, and the deep sea keeps no such secrets. Today, every probe and DNA test returns the same answer: absence. The real wonder isn't what hides in the trench, but how curiosity keeps us searching. What do you think drives that search? Share below.